We have studied a number of basic amplifier topologies so far. In all of these, we derive the input-output relationship using the small signal incremental equivalent circuit, which is linear. The input-output relationship is also linear. Now, the MOS transistor is really a nonlinear device, and we know that the linear approximation breaks down as the signal becomes large. Now, how large is large? It's a difficult thing to determine. Okay, as the signal level increases, what happens is that the nonlinear products go on increasing, and at some point they become so large that they are no longer tolerable. Okay, so that's how you say how large a signal you can apply to the amplifier or any other device without running into severe nonlinearity. Okay. So in an amplifier or any other electronic circuit, the maximum input amplitude is limited by nonlinearity. Okay, as the input amplitude increases, the nonlinear products increase. What it means is, for instance, if you apply Vp cos omega t to a linear device, the output will be a sinusoid at the same frequency. It may be phase shifted and its amplitude may be different. Okay, but there will be nothing else. There will only be a sinusoid at the same frequency. But if you do put it into a nonlinear device, we know that our amplifier is of course nonlinear. We'll have a component at the same frequency as the input, but we'll also have in general all the harmonics of the input. Okay, this would never happen in a linear circuit. Okay, and these are the nonlinear products. Now, as you increase the input signal level, these products will also increase. Okay, and at some point they become quite large, and basically you can't use the amplifier anymore. Now, how large a value of these nonlinear products can you allow? It very much depends on the context. It may be 1% of the fundamental, it could be 0.01%. So we can't make a general statement about that. Okay. So in general, what you do is you carry out a detailed circuit simulation, including the nonlinearities, look at the distortion products using usually Fourier analysis, and then you set some limit for the input based on the criteria that you have on hand. Maybe in some application you want the nonlinear products to have an amplitude that is 1 by 1000 of the fundamental, 0.1% of the fundamental. Okay. Now, such an analysis requires you to analyze the nonlinear circuits as it is. You can't use the small signal incremental circuit, which is linear. But we would still like to have a way of specifying a maximum signal that can be applied to our amplifiers. Okay, let's say you take the common source amplifier, you want to be able to say what is the signal level that you can apply. And more importantly, if you are comparing two different designs, let's say two people design a common source amplifier for the same gain, you want to be able to compare and say which one can accept a larger signal. Okay, that is more important. It's also important for design. Let's say you do all of this analysis and determine that you can apply a 100 millivolt input having the nonlinear products to be very large, and you want to know how to make it bigger. You want to be able to apply like 200 millivolts input. What do you have to change in the circuit? Okay, so this brings us to the discussion of what are known as swing limits of amplifiers. Since the actual limit is based on the nonlinear distortion products and they are very much dependent on the context, we will use the swing limits which can be specified without ambiguity for any circuit. Okay, and they are based on trying to keep the MOS transistor in saturation region. We know that our MOS transistor has to be in saturation region for it to behave like a good amplifier. Okay, so instead of trying to figure out how much the distortion product is, we simply look at the limits on the input signal which will still keep the transistor in saturation region. Okay. You can specify the limits in terms of the input signal or the output signal such that all transistors remain in saturation region. Okay. Now let's take the common source amplifier as an example. To avoid the voltage division between RS, the internal resistance of the input source, and this R1 and R2, I will assume RS to be 0. Okay, this doesn't change the discussion in any fundamental way. And let me use source feedback biasing, and I use a large capacitor so that the source terminal is connected to ground. Okay, and I have some RD and some RL. Okay, let me say that this is 50 kilo ohms and this is also 50 kilo ohms, and use a 15 volt supply. Okay, and this current source is 200 microamperes. Okay, and I will also assume that all capacitors are chosen correctly so that they behave like short circuits at the signal frequency. Okay, so if we have 15 volts here with 200 microamperes, there is a 10 volt drop across RD, and this voltage with respect to ground will be 5 volts. Okay, and I'll also assume that R2 by R1 plus R2 is 4 by 15. This means that the bias voltage at the gate of the transistor will be 4 volts. Okay, and you can clearly see that the transistor is in saturation region because the drain voltage is above the gate voltage. If the gate voltage is 4 volts, the drain falls below the gate by one threshold voltage. If the drain falls to 3 volts, it will reach the edge of triode region, and if it falls further below, it will go into triode region. Okay, so now it's very much in saturation region. And what is the source voltage? I won't work it out now. I am still assuming the same transistor as I've always assumed, which is a transistor with muon Cox of 100 microampere per volt square and W by L of 1 and a threshold voltage of 1 volt. So this means that for a 200 microampere bias current, the gate source voltage of the transistor will be 3 volts and the source is at 1 volt. Okay. Now let's see. Let's imagine that Vi is a sinusoidal signal and we apply the sinusoidal signal to the amplifier. Okay, this is the time axis. If I plot the gate voltage Vg, okay, the operating point voltage is 4 volts. Okay, so let me mark it somewhere over here. It's 4 volts. Okay, and over that we have the same signal. The total voltage here will be 4 volts plus Vi because I have Rs equals 0. So the signal at the gate will be something like that. this is Vg when the signal is applied. Okay. Now the drain operating point is 5 volts. Okay, so it is somewhere here. This is not necessarily to scale. Now what happens is, as Vi increases, Vg will increase, and as Vg increases, the source will be at a fixed voltage. Because the C3 is very large, it means that the source is incrementally grounded, and in the large signal picture what it means is that the source will be fixed at 1 volt. So you can think of C3 as being a very large capacitor that holds 1 volt, and it will keep it at 1 volt even when the signal is applied. Okay, all the criteria that we evaluated, that is the C3 must be much greater than Gm by omega and so on, it will ensure that this will remain at 1 volt. Okay, so this doesn't change at all. So as the gate voltage increases, the drain current increases. Okay, and as the drain current increases, the drain current will flow through Rd parallel RL, and the drain voltage will fall down. Okay, or you can also think of it as the incremental voltage at the drain is minus Gm Rd parallel RL times Vi, right? So the incremental voltage at the drain will be superposed on the operating point voltage, which is 5 volts. Okay, and it does that. Okay, it will be out of phase of the input, and that's how it will be. This is the total drain voltage. Now you can see that although you started off with Vd of 5 volts and Vg of 4 volts, at some point in the cycle the drain voltage falls below the gate voltage, and for a sufficiently large input signal the drain voltage could fall 1 volt or 1 threshold voltage below the gate, and the transistor can go into triode region. Okay. So that's when it goes out of saturation region, and we take that as the limit, the value of Vi at which the transistor goes into triode region. That is one of the limits. So as Vi swings up, it can go into triode region. And similarly in the other direction, as Vi falls down, you can see that the gate voltage is falling down. Okay, the source voltage is fixed. Now you know that the gate source voltage has to be above the threshold voltage for the transistor to be on. Okay, so it is possible that as the input swings negative, the gate voltage falls below 4 volts, and the VGS of the transistor can go below a threshold voltage. So then the transistor can cut off. Another way to think about it is, as the gate voltage reduces, the drain current will also reduce, and the drain current can go to 0. Once it goes to 0, there can be no further change in the output voltage because the transistor is cut off. Okay, so as Vg swings negative, here at these points the transistor can cut off, meaning it reaches the off state, right, when there is no current at all in the transistor. So that sets the lower limit for Vi, that is the negative limit for Vi. Okay, so there are two reasons why the signal that can be applied to an amplifier can be limited. One is because the transistor can be driven out of saturation region into triode region. The other one is it could be driven into cutoff. Okay, based on these two effects, we will evaluate the limits on the input signal. Okay, these are the swing limits of an amplifier.